Okay, so the ninth example is one that looks pretty daunting. As my pen has run out. Looks pretty daunting, but is a proof that's explicitly mentioned in the syllabus. So it is one that it's well worth you practicing if you can't follow it sequentially and logically. It's one that's worth you learning how to derive. But to be honest with you, it's quite a straightforward one to follow. There's a little bit of pure involved, which is one of the trig identities linking sec and tan. So we'll cross that bridge when we come to it. But again, there's a big clue in how that is written there. Right, so a particle is projected from a point with speed u at an angle of elevation alpha and moves freely under gravity. When the particle has moved a horizontal distance x, its height above the point of projection is y. Show that that particular expression there is true. So what are they giving us? Not a lot, you'll be thinking. So what we've got here is our particle. It's being fired off at an angle of elevation alpha and a velocity of u. Well, from that I know that that means that ux is cos alpha. Sorry, it's not, it's u cos alpha, and uy is u sine alpha. So I can write those components straight down. And then it's telling me that when it's moved a horizontal distance x, so this now is flying parabolic arc across, and at some point that we don't know, it reaches there, and that point has got a horizontal distance of x, and its height above the point of projection is y. Now if you look back at the equation there, I'm expecting you to recognize that that looks as if it's part of the s equals ut plus a half at squared family, because I've got a half there and I got the ay there. So I'm likely to be using this. And if I put in vectors all the information that I'm given at this point here with t equals t, I've got s equals u t plus a half a t squared. So that one vector equation is going to form a pair of simultaneous equations, and looking back at the show that, I can see that time does not feature in that equation. So from my simultaneous equations, I'm going to want to eliminate t to form a single equation. So if I consider horizontally, I have x equals u cos alpha t. So that's equation 1. And if I consider vertical motion, I have y equals u sine alpha t minus 4.9 t squared. So looking back at my show that, I've got y equals, and then I don't want to have t's, but I want to keep things in terms of alpha. So I'm going to rearrange 1 to give me t equals, and plonk that into equation 2. So from 1, t equals x over u cos alpha. in equation 2, y equals u sine alpha, and then instead of t, I've got x u cos alpha. Getting a bit excited now because I know from pure that sine over cos is tan, and I've got a tan in there that I'm aiming for. Minus, now the 4.9, if I look back at that, they haven't put in the 9.8, they've kept it in terms of g. So really I shouldn't have written that as 4.9, I think I should have left that as g over 2. So minus g over 2 t squared x over u cos alpha all squared. Right, so I can see that I can cancel those u's, and I know that sine over cos is tan. X tan alpha. Look at what I'm aiming for. The first part of the equation is x tan alpha. So I'm feeling pretty good that I'm on the right track here. Minus g x squared over 2u squared 1 over cos squared alpha. So I've squared top and bottom, and I'm isolating the trig part of it. So I got gx squared over 2u squared, gx squared over 2u squared. So all I need to be thinking about is how 1 over cos squared alpha ends up being 1 plus tan squared alpha. So there's 2 steps to this, and they're both from your pure work. First of all, knowing that 1 over cos is sec. So 1 over cos squared alpha is the same as sec squared alpha. And then the other trig identity is that sec squared is 1 plus tan squared. So also sec squared alpha is 1 plus tan squared alpha. So that 1 over cos squared I can write as sec squared, which I can write as 1 plus tan squared. Therefore, y equals x tan alpha minus gx squared over 2u squared, and instead of 1 over cos squared I can write 1 plus tan squared alpha, which is what they were asking us to show. So that is a proof that really you should, by this stage of year 13, be fairly confident that you can handle without having to learn it parrot fashion. So let's go back to the question. Where is the question? Show that y equals x tan alpha, blah blah, done, sorted. A particle is projected from a point A on a horizontal plane with speed 28 meters per second and angle of elevation alpha. The particle passes through a point B, which is at the horizontal distance of 32 from A and at a height of 8 meters above the plane. Find the 2 possible angles of alpha, giving your answer correct to the nearest degree. So what we're doing now is, if I just rewrite this, rewrite that, they're telling me now that u is 28, x is 32, u is 28, and y is 8. So there's a u there. I was wondering where we're going to use the 28. So substituting that in, all that information in, I get 8 is 32 tan alpha minus 9.8 times 32 squared over 2 times 28 squared, 1 plus tan squared alpha. If we now evaluate that big horrible fraction, so open bracket, fraction 9.8 bracket 32 squared close bracket over 2 open bracket 28 squared close bracket, that works out to be 6.4. So 8 equals 32 tan alpha minus 6.4 1 plus tan squared alpha. I can see a quadratic equation being formed. So clearing out this bracket, I get that. Negative squared coefficient, don't like that. So if I chuck everything over, I'm going to have 6.4 tan squared alpha minus 32 tan alpha, and then I've got 8 plus 6.4, which is 14.4 equals 0. So I've got a quadratic equation which I'm going to solve with my calculator, but this time it isn't going to be either x equals, it's going to be either tan equals. So either tan alpha equals menu polynomial degree 2 6.4 minus 32 14.4. So either tan alpha equals 4.5 or tan alpha equals 0.5. So those are the solutions of the quadratic. So now I've got to work out what possible angles that's going to give us now. Depending on how you've been taught, you might have been taught using cast, or you might have been taught using the sketch of the various trig graphs, which is the way I prefer to do it. So I know that tan, so that's 90, 180, 270, 360. The tan graph does this. So it's positive between 0 and 90. It's positive between 180 and 270. Well, my angle of elevation is between 0 and 90. So if I'm interested in 4.5, it's going to be an acute angle read directly off the calculator. So I need to go back into calculation mode, make sure I'm in degrees, shift tan of 4.5, 77 degrees. Or shift tan of 0.5, which is 27 degrees. So there are two possible ways that it's going to pass through. So what's happening here, depending on the point of projection, if the angle of projection, that's the point B, which is 32 across and 8 meters up. It's either going to climb steeply at 77 degrees and come back down like that, or it's going to be a much less steep projectile, and rather than hitting it on the way back down, it'll be rising to meet it and then going above it. So that's a real A-level standard question there.